Alright, so in this next video we're going to discuss the effect of row operations on determinants. In the last couple of videos we've seen that once you get to larger determinants, even 4 by 4, and 4 by 4 is not particularly large if you're using determinants for practical purposes. You might be dealing with determinants of size 100 by 100 or larger. For very large determinants, the cofactor expansion is not a very effective method. It's a very time-consuming, computationally intensive method for computing determinants because it's recursive. Even for like a 5 by 5 determinant, you'd have to calculate 5 4 by 4 determinants, which are given in terms of 4 3 by 3 determinants, and each of those 3 by 3 determinants is 3 2 by 2 determinants. So you're talking about 5 times 4 times 2, 60 2 by 2 determinants you'd have to calculate. We saw in the last video that if you have a triangular matrix, things are really easy because you just have to multiply down the diagonal. We also know that we can use row operations to get a matrix into triangular form. So if we knew what happened to the determinant when we performed a row operation, we would be able to sort of, get down to triangular form, calculate the determinant of that triangular matrix, and then go back and look at what row operations did we do and what were the effect of those row operations, and work our way back to figure out what the original determinant should be. That's going to be the strategy here. So, what happens when you do a row operation? Well, if you do a row operation of the first type, switching two rows, you change the sign of the determinant, right? So anytime you swap rows, you get a minus sign, and that's something to be careful of, right? If you're simplifying a determinant and you switch two rows, don't forget that there's a sign change. Now, what happens if you multiply a row by a constant? Well, if you multiply a row by a constant, that's the same thing as multiplying the determinant by that same constant. And that's easy enough to see if you expand along that row. We'll go over the the arguments in favor of these in a minute. The third one is a little bit harder to prove, and we're not going to go through the details. Maybe I'll show you that it works in the 2 by 2 case. This third type of row operation, where you add a multiple of one row to another, does not affect the determinant. And that's really useful because we know that that's the type of row operation that we use most often to create zeros. If we're trying to get down to triangular form, we're trying to create zeros, that's the type of row operation that we're going to use. And because that doesn't change the determinant, we can do as many of those operations as we want, and we know that the determinant of the resulting matrix will be the same as the determinant of the one that we started with. Okay, you do have to be a little bit careful about this. We'll warn you later on. A lot of you kind of write down row operations that are sort of like this third type, but not really. Right? A lot of you might try to do something like this. So you might do something like row 2 row 3 minus row 1, and make that your row 1. Okay. This is not elementary. Okay. This guy here is not elementary, but I know a lot of you like to do it, right? There's no real harm in doing this if you're using it to solve a system, but if you're using this to do a determinant, you've got a problem, because this is really two row operations. This is really row 1 minus 2 row 3 into row 1, which is a type 3 row operation, and then doing minus row 1 into row 1, which is a type 2 row operation. And this minus sign, right, that minus sign is really minus 1, right? Minus 1 times row 1, right? And multiplying row 1 by minus 1, well, that multiplies the determinant by minus 1, and you get a sign change that you might fail to account for. So be very careful about this. A lot of people will write down things like this. They get a sign change and they don't realize that they got a sign change, and so they end up with the wrong answer. They're off by a minus sign at the end. So this guy here, not an elementary row operation. Be careful of that. Couple of consequences at the bottom. One is, well, if you have a row of zeros somewhere, actually, I mean, the first one you don't really need to have this theorem to get the first right, because this one here we can just just expand along that row, right? So the first result already follows from our cofactor expansion theorem. The Laplace expansion theorem tells us we can expand along any row. So if you expand along a row of zeros, obviously the determinant is 0. But also, if one row of your matrix is a multiple of the other, the determinant has to be 0, because you could, if you have one row that's a multiple of the other, you could use a type 3 row operation to create a row of zeros and then expand along that row, right? And so then again, the determinant would be 0. All right. So a few examples. We'll just kind of see how this works. So if let's take a 3 by 3 matrix. Well, let's do 2 by 2 because I wanna calculate things quickly here. Okay, 2, 3, minus 1, 2. Let's say. Okay, so we know that the determinant of A is going to be 2 times 2 minus 3 times minus 1 is 7. Okay, so if I did if I swap row 1 and row 2, I get minus 1, 2, 2, 3, and then the determinant here, so let's call this thing, call it B. The determinant of B is going to be minus 1 times 3 minus 2 times 2, which is minus 7, which is minus the determinant of A. Okay, if I take my A and I do, let's say I do minus 3 row 2 to row 2, okay, 2, 3, 3, minus 6, and let's call that C. Well, the determinant of C is going to be 2 times minus 6 minus 3 times 3, so that's minus 12 minus 9, that's minus 21, which is minus 3 times 7, so minus 3 times the determinant of A. If I did the third type of row operation, let's say I did row 1 plus 2 row 2. I want to create a 0. 2 plus minus 2, 0. 3 plus 2, 2 times 2, so 3 plus 4 gives me a 7. Minus 1, 2, call that D. Well, the determinant of D is going to be 0 times 2 minus 7 times minus 1, which is 7, which is the same as the determinant of A. So we see that that row operation, it has no effect on the value of the determinant. Okay. All right. So let's proceed and think about, we've got this happening again. All right. Bear with me 1 second. Let's save. Let's close. Let's open. And there. Good. We're back in business. So how do we know that these properties work? How do we see that these results are true, that performing these row operations has the desired effect? Well, most of them are not so easy to see. The type 2 is actually the easiest one to see, and the easiest one to see in general. If I perform, if I have a matrix A and I perform, k times row I goes to row I, and I get this matrix B, right? So B is going to look like, what is B going to look like, right? It's going to be, right, so I'm going to have the original entries for A, and then somewhere in row I, I1, well, I'm going to have, that row is going to be multiplied by K, right? So I'm going to have K, AI1, all the way over to K, AIN, and then down to a n 1 and a n n. Okay, so if I was going to do the determinant of b, well, one of the things I could do is I could expand. I can go along row I, right? So I expand along row I, and I would get, well, KAI1 times the cofactor. Now, here's the thing. So really, I should say it's the I1 cofactor of B, right? And then down to KAIN, and then the IN cofactor of B. Okay, so there's two things we can observe here. One is that I can factor out a K. The other one is that the only row that I've changed is the row that I'm expanding along. So the cofactor is along row I. If I delete row I, right, then what I'm left with, the other rows are the same as the rows for A. So these cofactors along row I are the same as the original cofactors for A. So I get the I1 cofactor of A down to the IN cofactor of A, right, which is just K times the determinant of A. All right. Now, the other ones, kind of arguing in general, takes a little bit of work, and so we're not going to do the general proofs. But we can see that if A looks like, say, A, B, C, D, and if I apply, if I switch row 1 and row 2, and I get to C, D, and then A, B, okay, and let's call that thing C, then the determinant of C is going to be CB minus DA, which is the negative of AD minus BC, which is minus the determinant of A. So we see that it works for 2 by 2, and then you can, once you know that it works for 2 by 2, you can come up with an argument showing that it works in general, but it's a bit of a mess, so we're not going to do it. And similarly, if I did, let's say I did, let's just go here. Let's say I do row 2 plus K row 1 into row 2, okay, and then I would get, so I would get A, B, C plus KA, D plus KB, call that D, and if you calculate the determinant of D, you get AD plus AKB, when I do A times D and then A times KB, minus, well, BC plus BKA, and you can see that when you subtract this AKB and this BKA, right, those cancel out and you're left with the original determinant, AD minus BC. Okay, and with a little bit more work you can show that this also holds for 3 by 3 and higher, but we definitely don't have room to do that on these slides, and we don't want this video to get too long. Okay, so how do we use this to calculate determinants? Well, we use our row operations to try to get our determinant down to triangular form, because we know that determinants of triangular matrices are easy. Okay, a general rule of thumb here is that you should stick to that third type of row operation, because those ones don't change the value of the determinant. The other two types of row operations, they change the value, so if you must perform one of those row operations, then you need to kind of keep track of the changes. And I'll warn you now that these guys here, the second type, those ones are kind of tricky to keep track of, and so unless you absolutely need to use it, you should probably avoid it. Not that you can't use it, it's just that when you're trying to come back to the original answer, a lot of people get confused over, okay, I multiplied by 2, do I need to take my final answer and divide by 2? Do I multiply by 2? Which way should I go? And it's easy to get mixed up. So you can use them, but you got to be careful. And as I warned earlier, be careful that your type 3 row operations really are type 3 row operations. If you're doing something which is not an elementary row operation because you're adding a multiple n, changing a sign, you're going to end up with the wrong answer. Okay. All right. So let's do one quick example to see how we might do this. All right. So here's a determinant, and I want to find, or here's a matrix. I want to find the determinant of A. And I want to find it by reducing. So the first thing I'm going to do is I'm going to do this, row 2 plus row 1 into row 2. Okay. Now that's a type 3 row operation. So if I do that, the determinant of the resulting matrix will be equal to the determinant I started with. So 2 minus 4, 6, 0, 3, oops, sorry. So I'm doing 3 minus 4, so minus 1. And then 0 plus 6 gives me 6, 0, 4, minus 5. All right, so I create that 0. And now I want to get rid of the 4. So we could, if we wanted to, if we were worried about getting a leading 1, right? Notice I didn't bother to create a leading 1 in the first row. I could, but I didn't. So I don't worry about the 2 because I'm going to, I don't need it to be a 1 because I'm going to multiply down the diagonal to get the determinant in the end anyway. Similarly, I don't worry about the fact that this is minus 1 rather than plus 1. I'm not trying to solve a system, I'm trying to compute a determinant. So all I really need to do is get rid of the 4, and I can see that I can do that if I do row 3 plus 4 row 2, okay, into row 3. That's a valid type 3 row operation, and I get down to 2 minus 4, 6, 0, minus 1, 6, 0, 0. Now I've got to do minus 5 plus 4 times 6. That gives me 19. Okay. And now I can say, well, the determinant of A is 2 times minus 1 times 19. So I get minus 38. Okay. So that's how you would calculate a determinant using elementary row operations. Let me just do one thing here to kind of illustrate how things work if you did want to do one of those type 2 row operations where you multiply by a constant. If I did a row operation of the form 1/2 row 1 to row 1, because I did want to create a leading 1, and I noticed, hey, everything in row 1 is even, so I want to multiply by 1/2, okay? So if I did that row operation, well, when I multiply by 1/2, I multiply the determinant by 1/2, and so then you think, oh, I put a 1/2 out front, right? Ah, no. So let's kind of think about what this is, okay? So I can't quite say 0 yet, and so let me just say I'm going to do this row operation. A goes to the matrix B, which is 1 minus 2, 3, minus 2, 3, 0, 0, 4, minus 5. Okay? So the rule here is that the determinant of B is 1/2 the determinant of A. And that means that the determinant of A is 2 times. So this is where you can get mixed up, right? You might want to put the 1/2 out front when you do this row operation, but really what you should be putting out front is a 2. And probably the right way to think about it is simply that, in this row, you see there's a common factor of 2 in a row. If there's a common factor in one of the rows, you can pull it out. So you can just take that common factor of 2. So you say, look, this is 2 times 1, 2 times minus 2, 2 times 3, and so you just pull the 2 out front, and so you say, okay, so the determinant would be 2 times the determinant of 1 minus 2, 3, minus 2, 3, 0. So you can think of the effect of that type 2 row operation. You can think of it as pulling a common factor out of the determinant. That's essentially what you're doing there. Okay. All right. So we'll move on to some more examples in the next video.